everyone. You're watching the second part of the 30th video in the series Mathematical Methods for Economics. In this part of the video, we will be covering Newton's binomial formula, and we're going to look at how this comes about as a special application of the Taylor's formula. And as you're watching this video, if you start wondering how this is related, how this links up with the binomial formula that you studied in school, then we're also going to take you through the assumption which then gives you the result which you are used to seeing from your school algebra classes. So let's get started. Let's suppose our function is given by f of x equal to 1 plus x to the power m. And here m is any arbitrary real number. This is a crucial assumption because this is something we're going to drop at one point to see what result we get. Or we'll make it more restrictive. But for now, m is any arbitrary real number. We're going to restrict x, however, to be greater than -1 because we don't want to deal with negative numbers in the parentheses, because if you have a negative number in the parentheses and m is something like, let's say, half, then clearly you can't take the square root of a negative number. So we don't want to get into that kind of a territory. So we will take x as greater than -1. Okay, now if this is a situation, then the function f of x, the nth order Taylor's polynomial along with the remainder, which then gives us a Taylor's formula, as you've seen from the first part of the video. The Taylor's formula is given by f of x equal to f of 0 plus f prime at 0 times x plus 1 by 2 factorial f double prime at 0 times x squared, and so on till 1 by n factorial, the nth derivative at 0 times x to the power n. And then we have the remainder, which is 1 by n plus 1 factorial, the n plus 1th derivative at c, for c between 0 and x, times x to the power n plus 1. We've already covered this formula in the first part of the video. So let's quickly do our calculations. What is f of 0? F of 0 is 1. For f prime at 0, we'll first look at f prime of x, which is m times 1 plus x to the power m minus 1, which implies that f prime at 0 is m. Similarly, f double prime of x is m times m minus 1 times 1 plus x to the power m minus 2, which then gives us the second derivative evaluated at 0 as m times m minus 1. Now, let's do one or two more such derivatives, and you clearly see a pattern emerging. If you look at the third derivative of the function, that is m times m minus 1 times m minus 2 times 1 plus x to the power m minus 3. Now, I hope you're seeing a pattern emerge, because if you notice here, the third derivative at 0 is m times m minus 1 times m minus 2. The derivatives in general, they are taking this form where you are stopping. If you look at the factors, you're stopping at 1 less than the order of the derivative you're taking, and the power of 1 plus x is m minus the order of the derivative you're taking. Just note these 2 points. And if you look at the derivatives evaluated at 0, you're going down just that many steps, so that the last factor is m minus 1 less the order of the derivative that you're taking. So in this case, for the third derivative evaluated at 0, you have m times m minus 1 times m minus 2. Okay. Similarly, the nth derivative of x would be m times m minus 1, and so on till m minus n minus 1, like I said, 1 less than the order of the derivative we are taking, times 1 plus x to the power m minus n, so that the nth derivative at 0 is m times m minus 1 times m minus 2, and so on till m minus n minus 1. And to just give you just go one step ahead, because we'll also be writing down the Taylor's formula, so we'll need the n plus 1th derivative at c. So in that case, the last factor here would be m minus n. In this expression for the n plus 1th derivative, but let's see how these results fit in. So let's take a summary of the results here. We have f prime at 0 is m, f double prime at 0 is m times m minus 1, and so on till the nth derivative at 0, which is all the factors starting from m going up till m minus n minus 1, right? So we can write the Taylor's formula as f of x equal to 1 plus m times x plus m times m minus 1 divided by 2 factorial times x squared, because this term would now be the second derivative at 0 divided by 2 factorial times x squared, and then going on till m times m minus 1 and so on till m minus n minus 1 divided by n factorial times x to the power n. I've simply substituted these results above. I wouldn't like to use n plus 1 a derivative at 0. It should be n plus 1 a derivative at c. So that we'll look at in the next slide. But up till the nth order, we have the polynomial approximation here, and then to that we add the remainder r n plus 1 of x to get the Taylor's formula. That's our Taylor's formula. Okay, so let's substitute for r n plus 1 of x. Now we will go up till m minus n, because we're taking the n plus 1 derivative. So when we are taking the derivative at c, we'll have the factors m times m minus 1 going up till m minus n. In the remainder, we already had n plus 1 factorial in the denominator, and then we have 1 plus c to the power m minus n minus 1, right, because it's the n plus 1th derivative. So we subtract n plus 1 from m, which is m minus n minus 1 times x to the power n plus 1. So it'll be nice if you just write these steps down on a piece of paper and go through these steps yourself, because then you get a better understanding of the expressions. Okay, what we're going to do here is we're going to introduce some notation which you would already recognize if you've done permutations and combinations. So here we'll introduce a notation MCK, which some people also call M choose K. So MCK, which is to say that you go down these many factors, so m times m minus 1 and so on till m minus k plus 1 divided by k factorial. But remember here that k is a positive integer and m is, as we assumed in the beginning, m is any arbitrary real number. So MCK is this expression. Let's get a sense of what this math means. M minus k plus 1 here is a last term, m is a first term. So I'll just walk you through one or two examples to see how this notation works, and then we'll substitute this notation into the Taylor's formula above. Okay, so for example, if we are looking at 5C2, and all of you would know this if you've already done permutations and combinations in particular. So when you have 2 as here k is 2, right, 5C2 means m is 5, k is 2. So when you have 2 as k, that means you have to take 2 factors, you have to take 2 factors, go one step down. Okay, so 5 times 4 divided by 2 times 1. In the denominator you have k factorial, so that's 2 times 1. In the numerator, because you have k as 2, so you have to take 2 factors in the numerator starting from 5, because as I told you, m is the first factor. Okay, similarly, if I were to ask you to calculate half C3, so how many factors would you have in the numerator? Exactly 3. You'll go down, so you'll take 3 factors, which is to say you'll go down 2 units, so that you'll have in the numerator half times half minus 1 times half minus 2, and in the denominator you have 3 times 2 times 1. And why are we doing this? Because see, your k plus 1, when your k was 2, so m was 5, so 5 minus 2 plus 1, which is 4. So your last term here is 4. But the easy way to remember it is that you have as many factors in the numerator as k. Okay. Similarly, if you calculate MC1, that's exactly equal to m, okay, and MCM is exactly equal to 1. So that also you can check for yourselves, because if k is 1, then you're going to have m as a last term or the first term in fact. So that's going to be m itself and 1 factorial in the denominator, so that's m, and then MCM is similarly 1, which will give you basically m factorial divided by m factorial. Now let's put this notation in our Taylor's formula. So this then gives us a Newton's binomial formula once we write the Taylor's formula in this format, where m is any arbitrary real number and n is a positive integer. So you have 1 plus x to the power m, which is then written as f of 0, which is 1 here, plus we had f prime at 0, so that's MC1, okay, that was m, if you remember from the previous slides, mc1 times x plus mc2 times x squared and so on till mcn times x to the power n, and then you have the remainder, which is mcn plus 1 times 1 plus c to the power m minus n minus 1 times x to the power n plus 1. Okay, and this c again lies between 0 and x. We are taking x greater than minus 1 here. As mentioned earlier, the approximation would be better the higher the order of the approximation, or the closer x is to 0, and in particular we would want the mod of x to be less than 1, because then in that case we will be dealing with decimals between minus 1 to 1, and those will become smaller and smaller as you take the when you take the power as n plus 1. So let's take an example to see how we can apply the Newton's binomial formula. Use Newton's binomial formula to estimate the value of the cube root of 1.1, and here the question is asking you to take n equal to 2. Also the question asks you to find the upper bound to the error. This is something you should get comfortable with because this is important. So the underlying function here, because you have 1.1 cube root, right, the underlying function here f of x can be taken as 1 plus x to the power 1 by 3. So that when you put x equal to 0.1, you will get 1.1 to the power 1 by 3, right. So this is the underlying function. Now we know from, because we are taking n equal to 2, we know from Newton's binomial formula that 1 plus x to the power m is 1 plus mc1 times x plus mc2 times x squared. So we have to go up till n equal to 2, and then we have the remainder mc3 times 1 plus c to the power m minus n minus 1. So the n is 2 here, so m minus 3 times x cubed. Okay. So once we write down the Newton's binomial formula, we just have to plug in the information. We have m equal to 1 by 3 here, x equal to 0.1. So with m equal to 1 by 3 and x equal to 0.1, I can write 1.1 cube root as 1 plus 1/3 c1 times 0.1 plus 1/3 c2 times 0.1 squared. I am just substituting here, plus 1/3 c3 times 1 plus c to the power 1/3 minus 3 times 0.1 cubed. Okay, so this in turn, let us do some calculations here. 1/3 c1, our first term here is 1 on the right hand side, plus 1/3 c1 is nothing but 1/3. If you remember, I said mc1 is m itself, times 0.1, which I am writing as 1 by 10, plus 1/3 c2, which I have here, that's 1/3 times 1/3 minus 1 divided by 2 factorial times 0.1 squared, which is 1 by 100. Then for the remainder I have 1/3 c3, so 1/3 times 1/3 minus 1 times 1/3 minus 2. I have 3 factors in the numerator divided by 6, 3 factorial 6 times 1 plus c to the power minus 8 by 3 times 1 by 1000. So if I want an estimate of 1.1 to the power 1 by 3, ignoring the remainder, my estimate for 1.1 to the power 1/3 would be 1 plus 30, 1 by 30, plus, now 1/3 times 1/3 minus 1 is 1/3 times minus 2 by 3, the whole thing divided by 2, the 2's will get cancelled. So you get minus 1 by 9, which multiplied by 1 by 100 will give you minus 1 by 900. So the estimate that we get from the polynomial approximation for n equal to 2, the quadratic approximation for 1.1 cube root is 1.03222. If you go up to 5 decimal places, you can try this on your own. This can be even done by hand. And let us now look at the remainder for this corresponding approximation. The remainder is given by R3 of 0.1, right, which is 1/3 c3, 1 plus c to the power minus 8 by 3, 0.1 cubed for c between 0 and 0.1, which then gives me 1/3 times minus 2/3 times minus 5/3 divided by 6 times 1 by 1000, which is nothing but 0.1 cubed written out in this fraction form, times 1 plus c to the power minus 8 by 3, and this turns out to be 1 by 16,200 times 1 plus c to the power minus 8 by 3. Okay, so with this as the remainder, we can look at this expression, and again we are interested in the upper bound to the remainder. So you can see here that the upper bound will be this 1 plus c to the power minus 8 by 3. The upper bound is 1 here. It can also be seen intuitively by looking at this as if you put c equal to 0, that is the maximum, because c lies between 0 and 0.1, but because here c is positive, it takes on the maximum value when c is 0 actually. Okay. So the upper bound to this remainder is 1 by 16,200. Alternatively, if you can't understand the intuition that I am giving you, you can just do the mathematical calculation, because c lies between 0 and 0.1, 1 plus c will lie between 1 and 1.1, then raise everything to the power 8 by 3 and reverse the inequality. So you get the upper bound to 1 plus c to the power minus 8 by 3 as 1 itself. So I just have to multiply in the first step by 1, and I get my upper bound as 1 by 16,200. Okay. And again, this is a very nice estimation, because the true value of the cube root of 1.1 is 1.03228, and what you got from your estimation was 1.03222, which is very, very, very close. Okay. Now, what I'll do in the time we have left, let me make you understand a little bit how this analysis that we are doing is related to the binomial formula that you have studied in school. So, see, what you have studied in school is a plus b to the power m is equal to a to the power m plus mc1 a to the power m minus 1 times b, and so on till mcm times b to the power m, which is nothing but b to the power m. And here m, the difference now is that m is a positive integer. So far you were taking m as any arbitrary real number, now m is a positive integer. Okay. So if you go back to the binomial formula with m as an arbitrary real number and n as a positive integer, we have already looked at this formula. So the question is, how does this Newton's binomial formula connect with the formula above? Is there a way we can get at the formula that you are so familiar with from Newton's binomial formula? And the answer is yes. So what we are going to do is, let's take m, because the point here is that we want to look at a positive integer exponent. So we want m as a positive integer, and once we do that, you can see the result follows. So if I take the Newton's binomial formula for let's say 1 plus x to the power m, that's 1 plus mc1 times x plus mc2 x squared and so on till mcn x to the power n, and then the error. Now suppose I take m as 5, and for convenience I also take m equal to n equal to 5. Okay. Now what happens here? If m is 5, basically my function is 1 plus x to the power 5, and this then becomes, and because I am taking the order of the approximation as 5, I will go up till 5c5 x to the power 5, right? And then I will get 5c6 1 plus c to the power minus 1 times x to the power 6. Okay. The question is, what is this 5c6? So 5c1 you will calculate, 5c2 you will calculate up till 5c5. Now if you look at this 5c6, there is something interesting going on, because you are going to take 6 factors now in the numerator, because you are taking k factors, right? You are going down 5 steps. So 5, 4, 3, 2, 1, 0. So once you come down to 0, the whole thing becomes 0. The basic point that I am trying to make here is that in the combination mck, where m is a positive integer and k is also a positive integer, if k is more than m, then you will end up having m minus m also as a factor in the numerator. You can try it with any set of numbers wherever k is more than m, and try it out for yourself. So when you have m minus m or 0 to say in the numerator, then mck is equal to 0 for all k more than m. Now this actually then leads us to something very interesting, because if m is a positive integer, the exponent is positive, it's a positive integer, excuse me, the formula 1 plus x to the power m What will that boil down to? That will, and here we are taking m equal to n, let's say. So 1 plus mc1 x plus mc2 x squared and so on till mcn x to the power n. Take m equal to n, right? You're going to get mcm times x to the power m as a last term, which is what you were getting for a plus b to the power m also. And here b is x, a is 1. But what will happen to this last term? The last term will vanish because in this m c n plus 1 is going to be 0 because n plus 1 is more than m. Okay. So, what are the assumptions that we are making here? M is a positive integer, the exponent is a positive integer, and m is equal to n. Okay. So, therefore, if m is a positive integer, we can write 1 plus x to the power m as 1 plus mc1 times x plus mc2 times x squared and so on till mcm times x to the power m. In fact, you can even just manipulate the terms and get the exact formula for a plus b to the power m by simply putting x equal to b upon a. Now, once you put x equal to b upon a, what do you get on the left hand side? You get a plus b to the power m, right? And that a to the power m which you have in the denominator when you take the LCM, then that you can cross multiply all the terms on the right hand side with a to the power m, which will then give you the desired result, which is a to the power m plus mc1, a to the power m minus 1 times b and so on till b to the power m. So, there is a clear linkage between your Newton's binomial formula, which you saw as an application of the Taylor's formula, and the binomial formula that you do in school, right, under a certain set of assumptions. Okay. Now, let me also, because this is something I did not take up in the first part of the video, let me also give you a proof, a very specific proof of the Lagrange's remainder formula, specifically for n equal to 1. You can try and generalize this on your own with the help of the questions and the hints given in the textbook in the exercise section of Sitzeder and Hammond in chapter 7. So, what you have here is, if I take n equal to 1, my claim here is that I can write f of x as f of 0 plus f prime of 0 times x plus 1 by 2 factorial f double prime of c times x squared. This is precisely my Taylor's formula. So, this is what I will be proving. But to do that, to get there, let us define for x not equal to 0, f of x equal to f of 0 plus f prime at 0 times x plus 1 by 2 factorial s of x times x squared, where s of x is a function which is implicitly defined by this equation here, right. What we want to prove is that there exists a number c between 0 and x such that s of x is nothing but f double prime at c. So, this is where exactly your number between 0 and x, why do we take the second derivative at c? So, this is because s of x will, as we will just see in a bit, s of x ends up being the second derivative evaluated at c for some number between 0 and x. So, the way to go about this proof is, let us keep x fixed and define the function g for all t as g of t equal to f of x minus, and you have this expression in parenthesis, f of t plus f prime at t times x minus t plus 1 by 2 s of x times x minus t the whole squared. So, this is a function of t. Now, if you notice here, what is g of 0 and what is g of x? And there is a reason why I am looking at these values. See, 0 and x are kind of your end values. So, because the interval you are considering is 0 to x. So, if you look at g of 0, this is going to be given by f of x minus, just put t equal to 0, you will get f of 0 plus f prime at 0 times x plus half s of x times x squared. I have just substituted t equal to 0 in all these terms where t is there on the right hand side, okay. So, this is what we get. Now, if you notice here, this is nothing because this whole expression in parenthesis is nothing but f of x by assumption. So, we get to 0. Similarly, g of x is f of x minus Now put t equal to x, the last two terms here will disappear but once you put t equal to x, and you will just be left with f of x, so that is also equal to 0. Okay, what does this mean? Now once I have g of 0 and g of x both as 0, we have a situation like this. I have just taken an arbitrary curve here, and you can apply what is known as a mean value theorem, which you must have done in school, that if you have a function which is continuous in the closed interval 0 to x and differentiable in the open interval 0 to x, then there exists some point. So basically I have a situation like this where the function is given in yellow here, and it is continuous in the closed interval 0 to x and differentiable in the open interval 0 to x. So what I can do is, since the value of g of 0 and g of x is 0, I can connect both these points, the values of the two functions, we can connect these two by a straight line, a line segment, and you can see here the slope of this line segment is 0. What we are saying, the mean value theorem, what the mean value theorem is saying is that I can always find some point on the graph such that if I were to draw a tangent to the curve at that point, the tangent would be parallel to this line segment that joins the two endpoints. And this is exactly what we have here. In fact, this is just one point. If there were more bends in this graph, there could be more than one point, but anyway, this is just to illustrate. So if you have a situation where the end values are 0, then by the mean value theorem, there exists a number c strictly between 0 and x such that g prime of c is equal to 0, because the slope of this tangent is going to be 0. And what is g prime of t? You can calculate it to get this expression here, minus f prime of t plus f prime of t minus f double prime of t times x minus t plus s of x times x minus t. So if I take g prime, because by the mean value theorem there exists a number c such that g prime of c is 0. So once I put t equal to c, I get, because these two terms will vanish in any case, I have minus f double prime of c times x minus c plus s of x times x minus c is equal to 0. And once you solve for s of x, you see that you get nothing but f double prime at c. So this is then the proof of the Lagrange's remainder formula, that that expression that we had left as an unknown in the functional form for f of x, that then turns out to be f double prime at c, and then you get the remainder term, the remainder formula. So I will just now, because we are running out of time, I will just leave you with this question which you can try on your own, where you have to use Newton's binomial formula. It's a quadratic approximation to approximate the value, find the approximate value of 28 to the power 1 by 3. But remember, because x has to be close to 0, you will have to write 28 to the power 1 by 3 as 3 times 1 plus 1 by 27 to the power 1/3, and then just go through the same set of steps that I have illustrated in example 3, and you will be able to get your result. So 28 to the power 1/3 is turning out to be approximately 3.03657, which is again very close to the true value. In fact, for most functions, the Taylor's approximation is very accurate and the error terms are very small. So here also we get the remainder as 1/3 C3 times 1 plus c to the power minus 8 by 3 times 1 by 27 cubed, and this if you look at the upper bound, this turns out to be 5 by 27 to the power 4. You can take screenshots of these slides and then do these calculations on your own, but this is a good problem for practice, so go ahead and do it. And that's all we have for this segment. Thank you very much.